the non-invasive phase margin measurement.
Well, and as always, this meeting will be recorded, so you will have the possibility to access this video afterwards via streaming, or in the worst case, if streaming is not working, we can also provide a download. In addition, we will provide the presentation in a PDF format so that you can also have a look at it later on. So, and now we start but before we touch base on stability measurements, we will have a look at the topic. For those of you who have not joined yesterday for the standard stability measurement stuff, what is stability? So when we are talking about stability, we have to talk about control loops. And a control loop is stable if the feedback that arrives at the error amplifier is 180 degrees, is in phase with the signal that gets into the error amplifier, because the error amplifier has a small minus, so it subtracts the signal that is coming back via the feedback loop from the input signal. And so if the signal arrives in phase to the error amplifier, it's then phase shifted and cancelled out. And so we have, this is why it's called the negative feedback, and so the whole system is stable. If the system arrives 180 degree phase shifted at the error amplifier, the minus in the error amplifier causes the signal to be in phase with the input signal, and as a result, we get a higher signal, and so we have an instability and we go into oscillation. The two things we are looking at in this seminar is the phase margin and the gain margin. When we talk about stability, this can be either shown in the so-called Nyquist plot. The Nyquist plot allows us to measure the distance from the gain curve to the instability point at -1. The distance between the instability point at -1 and the gain is the so-called gain margin. And because here the signal is in phase with the instability, and if we check where the gain is 1, which means 0 in the Bode chart, there we can measure the so-called phase margin. Most of you know this from the Bode plot. The only thing is, in the theory we reference to -180 degree, but this is caused due to the fact that we are looking at the signal at the input of the error amplifier, and the minus is not taken into consideration. If we break the loop in the feedback loop, so if, for example, at the position of the feedback divider, then the error amplifier is inside the transfer function we measure, and therefore we have to reference to 0 degree. So that's it roughly in a nutshell, because this is not the main topic for our presentation today, because we want to talk about the plan B. Our plan A is the signal injection method into the feedback loop, which has been elaborated on yesterday in our webinar about standard stability measurements. And there you can find everything in the PDF if you haven't been there, or in the recording. The other option that we are offering is a so-called non-invasive measurement. Non-invasive in the way that you are measuring the output impedance, you derive certain parameters of the output impedance, and then you are able to calculate the phase margin. To do so, you modulate the output current of the power supply, and this you do with the, for example, with a current injector, which we use from Picotest. Steve has designed this current injector exactly for these measurements. And so we can hand over to Steve, who will now give you a background on the non-invasive stability measurement.
Thank you. So there are many reasons that we might want to make non-invasive stability measurements, but the basic reason for doing so is the inability to access the feedback loop in order to directly measure the Bode plot. There are many examples, but just a few are integrated point-of-load regulators that don't have external feedback, fixed voltage regulators, voltage references, high bandwidth op amps, integrated switching regulators, many of these devices are either too small or don't provide access to the voltage divider, which would allow us to measure the Bode plot. And so I've included just a couple of schematic examples here that show 3 terminal devices that only have input, output, and ground pins, and no place to provide an injection signal. And yet in other places, there might be a prohibition to measuring the Bode plot because it would require either removing components or cutting printed circuit board traces. Next slide. So how does non-invasive stability margin work? You may be familiar with the work of Dr. R.D. Middlebrook, who popularized a topic called minor loop gain, which is generally represented as T sub M. And he introduced this through his extra element theorem that allows us to assess the stability of switching power supplies when they're combined with input filters. Minor loop gain is based on Nyquist criteria, and it's currently one of the most researched power electronics topics. You can find many of these articles by doing an internet search on a topic called Forbidden Region Stability Criteria. The concept is very simple. We break the system into 2 parts. We measure the impedance of the left circuit, we measure the impedance to the right circuit, and then the loop gain is measured as the ratio of ZS over ZL. And coincidentally, this is also how we measure stability of very large systems with black boxes. We measure the impedance of each black box, and we can calculate the stability of the connected system as ZS over ZL. Now, one note is that we can solve for the phase margin by setting the magnitude of that ZS over ZL equal to 1. Sorry, that's very fine print. Okay, next slide. So how do we separate a regulator into ZS and ZL? Unfortunately, they are connected, but we could call the regulator side of the circuit ZS, and we can call the capacitor side of the circuit ZL. Unfortunately, we can't actually separate those 2 elements on the circuit board. So what does the non-invasive stability margin method do? It extracts data from impedance and group delay that allow us to mathematically separate the ZS and ZL terms so that we can use minor loop gain to divide ZS divided by ZL in order to properly account for what it is that the stability is from an impedance measurement. We can measure it using 2 different cursor methods. There's a 2 cursor method that provides 3 data points required to accurately calculate the stability margin of the regulator, while a 1 cursor method only provides 2 data points. So that the 2 cursor method is always precise, while the 1 cursor method provides good results up to about 35 degrees of phase margin. You can learn a lot more about power-related measurements, including the non-invasive stability margin, from my new book called Power Integrity. It's available from McGraw-Hill, and it actually was just released this week.
Okay, thanks a lot, Steve, for your part of the presentation. We will keep you unmuted, but because I'm pretty sure we'll get additional questions, and you are the specialist on this topic. So in case we have a glitch or something in our presentation, please feel free to step in. Hast du jetzt ausgeschaltet? Okay. So, how to measure the output impedance of a power supply? There are several methods to do so. First, we have the possibility to do this by modulating the output current. And so we can do this by connecting the power supply directly to the output of the Bode 100. This is something we only recommend for power supplies with an output voltage of, let's say, 3 volts or 3.3.
3.3 maximum.
3.3 maximum. Lauren is afraid about the Bode 100.
Yeah.
Yeah, but in any way, not so many output amps have been killed so far. I think we have 1,200 out in the market, something like that, and about 5 have been killed, the ones we know of. Maybe some people repaired them themselves. So in any way, the point is when you do this one-port measurement, as we explained yesterday in our impedance seminar, it's recommended for impedances down to 0.5 ohms, but usually power supply has a much lower impedance, output impedance, and therefore we can use the shunt through method, which allows to measure even lower. But again, also here the limitation applies that you should not go above 3.3 volts.
Well, and the method we will show today is by using the Picotest current injector, the J2111A. And one reason why we use this injector is because it makes all the measurements very simple. It has an included current monitor, which we connect to channel 1, and at channel 2 we connect the voltage probe to the output of the power supply, and the current injector draws a small signal proportional to the output of the Bode 100, and as we sweep the output over the frequency range, then we get the current over the frequency range. By dividing the voltage over the current, we get the impedance of the power supply. Well, this works fine for power supplies that deliver current up to 10 amps, maybe something like that, or a little bit less. If you need very high voltages and very high currents, then then it can be that the Picotest J2111A is not strong enough. Picotest offers a second injector, the high current injector, that is the 2112. Bernhard, is that correct?
Sorry?
That's correct.
That's correct, Steve?
Yes, that's correct.
And it has a voltage limitation of 11 volts, I think, Steve. Is that fine?
That's correct.
That's correct. So in case you need even higher voltages, then you have to build your own amplifier. At the moment, we don't have one, or you're looking for current amplifiers that are available on the market.
Right.
Yeah.
Just one note, and that is that many electronic loads can also be modulated, and they can be modulated by the Bode 100.
Yes, that's true. However, we have found that most of the electronic loads have a frequency, an upper frequency range of 400 Hertz, which is not a lot. But probably if you find a very good one that goes up to 200 kilohertz, then it would be fine. Yeah. If you know one, Steve, then it would be nice if you can send us any information.
Yeah, that's a good point. Yeah, that's a good point. There is one electronic load that I used in my book, and that had a bandwidth of 65 kilohertz.
Oh, great.
And so you'll find that in the impedance chapter.
Okay. So again, some details about the 2111. The frequency range is from DC to 40 megahertz. So that's the very nice thing about the current injector, about the Picotest, that it goes up to 40 megahertz. And you can also do small signal step load testing with the 2111A, because it has a very very low rise time, so very
20 nanoseconds, I think.
Sharp edges. And it's usable for power supplies with output voltages up to 40 volts, and includes the current monitor output, and that's the nice thing.
So you don't need a current probe. You can just connect the current sensor output directly to the Bode 100, and it's normalized on the 50 ohms that the input impedance you can select for channel 1, and so you get 1 volt per amp, so you get a direct measurement. You don't have to worry about any correction factors and so on.
Okay. You can add a DC bias of 24 or 25 milliamps, and we need that since the Bode 100 output voltage is, how do you say?
That's not providing a DC offset.
So it's AC around 0, so we have a plus and minus sine wave, and the current injector is a current sink, so it cannot deliver current into our device on the test, and we need to sink current. We cannot source current. That's why we need the DC offset, but the current injector does provide it. The maximum AC current you can modulate is 48 or 50 milliamps peak.
Okay, we got a question that says, what if my converter output voltage is 41 volts?
Steve, please.
That's a very good question. I suppose then you would be out of luck. At 41 volts, it would probably still be okay. I can tell you that the transistors that we use in the J2111 are 65 volt transistors, but we do want to maintain adequate derating, and we also want to try to keep the power dissipation low. So one of the things that I suggest to my customers is that you can insert a small series resistor, and that would reduce the voltage at the current injector by the product of the 24 milliamp bias current and the inserted resistance. So that's a good way to reduce the voltage at the current injector, is to add a series resistance.
Okay. Okay. Thanks a lot for answering this directly. It's pretty cool.
The measurement setup. Bernhard, do you want to present the setup?
Yeah, well, in fact, it's not really difficult because I already mentioned a lot of it. We have our device on the test, which is either a linear regulator or a switcher. And at the output, we have our load connected. So the output filter and the load, this is important because we want to measure our device under standard operational conditions. And now what we do is we connect the output of the Bode 100 to the oscillation input of the PicoTest signal injector, and now we connect the output of the PicoTest signal injector to the output of our switcher. And now the signal injector starts to pull 24 milliamps, and by modulating the output of the Bode 100, we modulate this current. The nice thing about the PicoTest injector is that it has an inbuilt current monitor. So we just connect the current monitor to channel 1, and so we measure the output voltage at the channel 2, and we measure the output current in channel 1, and if we divide channel 2 by channel 1, we get the output impedance.
Well, you need to set up the Bode 100 correctly as far as I know, and I think that's on the next slide.
Yes, it is, and so please go ahead.
Yeah, if you want to measure the output impedance with the Bode 100 in this setup, then the first thing you need to do is you need to activate our external reference, such that the receiver 1 is really connected to the channel 1 connector at the Bode 100 front end. And then we terminate the channel 1 with 50 ohms by clicking on this switch, this little switch. Then the 50 ohm will be connected to the channel, and it will be terminated. For channel 2, please do not terminate with 50 ohms. Since we are connecting channel 2 to a DC voltage, the 50 ohm resistor is not designed for being connected to DC volts. So
yeah, it can withstand a little bit more voltage than the output of the Bode 100. But again, also sometimes we have to use probes if there are higher voltages. So, and if we use an oscilloscope probe, it's supposed to be used with 1 mega ohm, and therefore please keep the 50 ohm open, and then the input of the Bode 100 behaves like an oscilloscope input.
All the measurements we are showing now are done in our normal frequency sweep mode. This is our normal vector network analyzer mode where we can set all these settings. And
so how to set up the traces for this measurement? As Florian has indicated, we are measuring gain, so we're measuring a transfer function. Therefore, the measurement for both traces needs to be set to gain. And the next thing is, if you want to see the output impedance in dB ohms, then you choose magnitude dB. If you want to see the output impedance in ohms, you just choose magnitude, and then you can use a logarithmic scaling for the y-axis of trace 1, so that you can still see the same curve, but then the advantage is that you can use your cursor directly to measure the impedance in ohms.
To read the impedance value.
Yeah. The trace 2, you can set to gain as well, and then the format is either phase, if you just want to look at the phase of the output impedance, or later on, for the measurement of the non-invasive stability, it's important that you switch it to the Q factor of the group delay. So that's the setup we do. And now let's continue. I would like to introduce the two calculation methods that Steve has already mentioned a little bit in the beginning. So we are offering two calculation methods. One, the basic phase margin calculation, sorry for that, somehow I'm losing words now and then. The basic phase margin calculation is implemented in the Bode analyzer suite since 3 years now. It's used to get a quick stability impression, is recommended for low phase margin values, so it delivers accurate results for phase margins below 35 degrees. So this method can be easily used to find out if a circuit is stable or not. But if you have a stable circuit and you want to get a feeling about the stability margin, we recommend to use the two-cursor phase margin calculation. This is implemented in the new Bode analyzer suite 2.43 SR1, which will be released, Florian?
Next week.
Next week. Okay. And there it's more accurate for phase margin values above 35 degrees. And there, while the single cursor method is only using the Q of TG, we are using here the Q of the group delay and the output impedance measurement. To activate these phase margin calculations, you just go to the cursor grid of the Bode analyzer suite, you right-click into the cursor grid, and then you can choose either the basic or the advanced phase margin calculation method. So, and this leads us already to some measurements. Our device under test is the VRTS 1.5 demo board that Steve designed for us. A VRTS means voltage regulator test standards. Yeah. And it contains a linear regulator and 2 switchable capacitors and a load. The one capacitor is a tantalum capacitor with a low ESR, and the other one is an aluminum capacitor with a high ESR. We also have a resistive load and a LED. This LED is always connected, so it's a basic load. And Florian, how many milliamps does it take roughly?
I think it draws also roughly 25 milliamps. So if we add our injector, the current injector, the BicoTest 2111, then we will have a total load of 50 milliamps if we don't add the load resistor.
And this board is nice to do both types of measurements. So you can do the non-invasive measurements, which you can do, in fact, for every circuit. And we have a 5 ohm injection resistor at the top of the board in the feedback, above the feedback, between the feedback divider and the output voltage, which allows us to also do a standard stability margin, standard phase margin measurements. The nice thing is, every attendee of this webinar who sends us an email to info@omicron-lab.com will get one of these VRTS boards. So, the people that watch the recording, sorry, you have not participated in the webinar. Only the people that have been here with our live webinar get one for free.
Okay, Bernard, I think we will now step into the live measurement. And I would ask you to bring the camera on the screen.
Okay, I'll do so. Is it this button? Yeah.
Yeah. Okay, so we do already see the board here, and maybe you can draw the connections.
Yes.
To indicate the connections.
So we have the output of the Bode 100.
The annotation.
Ja. So, du kannst das so, was Bode auch noch sieht. Und gleich weiter vorkommen. Before I know this number, maybe. So, just a second.
Okay, now you see everything.
Okay, so the output of the Bode 100 is connected to the oscillator, to the modulation input of the current injector, and the output of the current injector, which is the current sink, is connected to the output of our board. In parallel, we connect a probe at the output of the board, which is connected to channel 2 of the Bode 100, so that we pick up the output voltage. And to measure the output current, we just have to connect the current monitor to channel 1 of the Bode 100. So we divide voltage by current, and as a result, we are measuring impedance.
And I will now switch on the board, and you can see our pretty blue LED lighting shining.
So, what's a blue light? What does it do?
It lights blue.
It glows blue, okay.
Okay, so let's start a new Bode analyzer suite to...
you need to switch off annotations first, yeah.
Okay, I'm now starting the Bode analyzer suite, and we just will directly go into the measurement now. Takes a second to start up, and that's the picture you see when you start up the Bode analyzer suite. And as I mentioned before, the first thing we do is we switch the receiver 1 to the external reference and terminate channel 1 with 50 ohms. And then we are done in here. The next thing is I would like to see the output impedance directly in ohms on a logarithmic Y scaling, and I also want to measure the phase of the impedance. And then to get a picture I'm used to, I will switch the sweep mode to logarithmic. And we will start at 100 Hz, since below 100 kHz there are the interesting things to see. Okay, so there is still quite some noise on the curve, and we have many possibilities to get rid of that noise. Bernhard, what would you suggest to reduce the noise in our
always curve? More power.
Okay, not always more power,
yeah.
But in this measurement we can do more power. It doesn't affect the system that much as in the injection, the voltage injection, the loop gain measurement. So we now give full power here, 13 dBm, that's the maximum power of the Bode 100 output, and we see that the result already looks a lot cleaner. What we can do in addition is we can reduce the attenuators on channel 1 and channel 2. The reason why we can reduce it is that we can see here on the overload indicator on the right hand bottom side that we nearly have no signal on the ADC. So we can reduce the attenuators to have more signal on the ADCs to get less noise on the result. And what else? You can also...
Yeah, if you want to slow down the measurement a little bit, you can reduce the receiver bandwidth. So there is the receiver uses a narrower filter, so it needs a longer time to settle. But the advantage is that the sum of the noise that you measure is less in relation to the useful signal, and therefore also your signal-to-noise ratio power-wise is reduced.
Okay, but I think here I will just keep it or let it set to 1 kHz. With the switcher, we will then see that the receiver bandwidth is very important since we have a lot more noise in the switching system. What I will do in addition is I will now set the start frequency to 10 Hz such that we see the area where the regulator is really not delivering or not looking like an inductor, but like a resistor.
So I think in this measurement we already see that there is no real peak in the output impedance. I think we have activated the electrolytic capacitor. So let's switch to the tantal capacitor. This will give us a more significant peak in the output impedance, please.
Bernhard, do you want to store the curve we have currently into the memory?
Yes, I'll do so. And activate the format, sorry, wrong button, data and memory. So now please switch to the tantal capacitor. So, and you see this tantal capacitor has a higher Q because the ESR is lower, and therefore you can immediately see this peak.
And Bernhard, one question, what's that in the phase? Why is the phase jumping that much below 10 kHz?
The phase is not jumping. Well, in fact, in reality, this is a continuous phase. The thing is, at the moment, we are in the wrapped phase mode. This means that the phase is dropping below minus 180 degree, and therefore it's wrapped up to 180 degree. And then here it's going above 180 degrees, so it's wrapped down again to minus 180 degree. We can overcome this by activating the unwrapped phase, and we say optimize, and now you see that we have a nice continuous phase curve. Nevertheless, when we look at the curve, we see that we have a flat curve here in the beginning. So this means that our power supply is resistive. So what phase shift would you expect for a resistive behavior?
Yeah, actually 0, and not minus 180.
Yeah, and so we also had a look on this, and the reason why we are measuring minus 180 is because the injector is a current sink, so we are pulling out the current. If the current would go the opposite direction, we had a plus 180 degree, and we would be at 0. So the only thing we need to know is that our new 0 is minus 180 degree. So everything which is above 180 degree is inductive, and everything which is below minus 180 degree is capacitive. And this matches exactly with the way the magnitude is changing. So we have flat for resistive, then we have an increase 20 dB per decade for inductance, then we have a peak, and then it drops down again, so it's capacitive, and then it starts to become inductive again. So these things match together as soon as you draw a line at minus 180 degree.
But before you were mentioning this QTG.
Yeah, the QTG we require to measure the phase margin, to derive the phase margin from the output impedance measurement. And you know that the TG is the first derivative of the phase, so it tells me how steep the phase is, how steep the phase curve is in a specific point. And so when we do this, we can find out that the steepest point of the phase is here in this area where the cursor is at the moment, and therefore we can activate the QTG. So the Q factor also has to be high at this point because it's a steep TG.
And that's always something that I like to, when I want to get the picture of this method, then I always think about a second order system and the phase shift and the phase turn of a second order system at the point of resonance. And if the phase turn is very high or very sharp, then you have a high Q, and high Q means a high possibility or a good oscillation possibility, which means very low phase margin. And of course the opposite around, if you have if the phase is turning very shallow, then you have a very low Q, and low Q is directly related to high phase margin.
We have one thing in the chat. Someone has lost the audio. If you have called in with the regular phone, please disconnect the phone line. So just put down your cell phone or regular phone and try to call in again. So hopefully this will help. Otherwise, the recording will be available.
Well, if it doesn't connect audio, then you can't hear our hints.
Okay, so then please type it into the chat while I... You're right. Okay, it's late now, at least in Austria.
Yeah, it's our 10th webinar.
Our 10th webinar, yeah.
I'll write it here.
Okay, excellent.
Bernhard, can you maybe start with the non-invasive phase margin measurement?
Yes, definitely, before we run out of time. So the only thing I want to do before I do this, I remove the software again, and I just show you what we measured. We measured some invasive stability with the voltage injection method yesterday. So we activated the electrolytic capacitor, and there we got a pass-through frequency at 8.4 kilohertz. So the 0 dB was at 8.4 kilohertz, and we achieved a phase margin of 76 degrees. And then we used, we had a dental capacitor activated. There we got a 0 dB frequency of 6.7 kilohertz and a phase margin of 37 degrees. And then we activated both capacitors. And now, since one has a high ESR and one has a low ESR, these ESRs are now in parallel. Also, the capacitance adds up. And so, in total, we get a capacitor which has a better Q than the aluminum capacitor, the electrolytic capacitor, but a worse Q than the dental capacitor. And as a result, the phase margin should be in between. And it was in between. It was roughly around 43, 44 degrees. So this was what we've done. Now there is a question that is, can this method be used on AA batteries?
Yes, it can, and we have an application note on our webpage where we show how to measure the output impedance or the inner impedance of a battery. And it's available on our webpage, www.omicron-lab.com, under the Bode 100 application area. section. If you can't find it, just send us an email at info@omicron-lab.com, and I will send you the direct link for download.
Yeah, and further on, we have a search function on our web page, so if you enter battery, you also should find it. In total, we are offering roughly 25 to 30 application notes, and there is another great source for articles and application notes, which is the www.bicodesk.com page. There you can find all the works of Steve, who has written many, many articles on many power-related topics. Yeah, and for sure, rechargeable batteries also work.
Okay, Bernhard. So let's continue with the
Where is the measurement? Yeah, I just want to show what we measured invasively so that we afterwards can compare.
Yeah, perfect.
So now we go back to the Bode analyzer suite, and we have here our dental cap. So for the measurement, this is the dental capacitor. Now we activate the Q factor of the group delay, and in the beginning we don't see anything, so we switch on the logarithmic scaling for trace 2, and now we can see immediately that there is a peak which is very close to the peak we see in the output impedance. So let's activate the cursor and set it to the peak of the QTG, and we can now see that the output impedance here is roughly 342 milliohms for sure. And now I right-click into the cursor grid, I activate the basic phase margin calculation, and we get a phase margin of 39 degrees. We just showed on the other slide that we measured 38 degrees. So this was a very quick measurement I did yesterday just to get the slide. So this is a quite nice fit. So, and this is with the single cursor method. So we are pretty happy with that one.
So Bernhard, if it's that easy with the single cursor method, why should I use the two cursor method?
Well, the higher your phase margin get, the more the two peaks will move away from each other. And as a result, if you just go to one peak, you do not get the complete truth. The distance between these two peaks is also in the secret formula of Steve. Okay. And therefore, the two cursor method is something that is recommended if you have phase margins, let's say in the range of 50 or 60 degree.
Before you said if we switch on both capacitors, then we will have something with 43?
44, 45.
45 degrees?
It was a crappy measurement I did yesterday, sorry for that.
Okay, I will switch on both capacitors now.
Yeah.
And then we can, maybe we see the effect of the two peaks moving away from each other, so we get the distance between the QTG peak and the impedance peak.
Now, first of all, we have seen that both peaks move down. This correlates with the fact that the 0 dB frequency, so the frequency where the gain curve crosses the 0 dB line is slower when both capacitors are activated. So, and now we will zoom in a little bit so that we get a better view on the maxima. And now I will activate both cursors, and I will activate the advanced phase margin calculation. Now, these peaks are still very close together. Nevertheless, we have to move the cursor into the center of each peak. So this, and here you see that if I do so if I want to get a symmetric peak on both sides, so I put it into half, then I see that I have two different values. Mm-hmm. And now I measure a phase margin of 46. So I measure to something around 44. So this is also a very good fit. You have to take into consideration that we just switched this on and did not look into any special details about this measurement.
We got a question. Is there a peak search feature, or did I miss it?
No, there is a peak search feature. However, the problem is that the peak search feature always jumps to measurement points. And as you can see, here you already can see that there are the single measurement points. And between the measurement points, there is linear interpolation. So if I would use the jump to peak function, it would jump to one point, but not necessarily to the highest point.
And also not, yeah, not to the highest necessarily,
yeah,
but not to the center of our peaking. And we want to have the cursor at the center of our peaking, so that the shape of the curve is symmetric on both sides. And since we have not that many frequency points in the curve, then the cursor will probably jump to a little bit more to the left, or if there is noise on it, a little bit more to the right, and this will already falsify our measurements.
And therefore, we do a kind of an optical thing. But standard, you just go close to the curve, you say cursor 1, and you say jump to maximum. Yeah, but for this, yeah, we can do it. And then this comes closer together, but now you see it's no longer symmetric. Yeah. Therefore, this is not the correct position, and also your measurement result is now further away from what we measured invasively. So I have to pick this cursor again, and okay, I just screwed it. Oops, here we are. So I put it to the center again with the optical, and that's it. Yeah, so sometimes it's better to do it manually. Okay. Good.
So let's also demonstrate the switcher, or do you have any other plans with the VRTS 1.2?
I think what we can show is what happens if we have a really, really good phase margin.
Yeah.
So if you just activate the activate the electrolytic capacitor, then we can show that it becomes a little bit more tricky to find the correct position of the peaks.
There are no peaks, in fact, anymore. Can you maybe reset the axis such that we see the picture? And I will now switch off the tantalum capacitor such that only the aluminum capacitor is switched on. And immediately we can see that the curve doesn't show a peaking anymore. We have already shown this curve before, but now we can recognize that if there is no peak, then we are looking at a very stable system.
Mm-hmm. So and now the situation is that I can somehow get the peak here for the QTG, and but I cannot do it for the output. So what I will now do is I will first switch back to just a second.
Okay.
Now I just killed it. So if I go to the single cursor method first, what I will just get a reading bigger than 71 degrees, which definitely fits what I've measured yesterday. They are measured 76 degrees. So and now if I activate the second cursor, I can switch to the two cursor method, the advanced method, and now I will first move the number 1 to something where I think there might be the peak, and the other one again, but nevertheless the reading also remains at bigger than 71 degrees, which is absolutely fine because this is what I measured. If I move it to a wrong position, then maybe I will be able to see some, now I would see 66 degrees, but this is not correct because our peak is here in this area, and then we again get the bigger than 71 degrees.
Well, sometimes people ask us, why do you only show the result up to 71 degrees? Why don't you measure more? And the reason is that we cannot measure higher than 71 degrees since the system is already damped that much that no oscillation will occur, and we cannot measure a peaking. So if there is no peaking, if there is no oscillation, then we cannot really measure the phase margin with this method. But if I know that my system has more than 71 degrees of phase margin, then I'm already quite happy with that.
Okay. So, we have now looked at the linear regulator, and I think it's very interesting for people to see that this method also can be used for a switcher.
Okay.
So, will you introduce the switcher while I do the changes?
However you want.
Oh, or I do introduce the switch and you do the changes.
Okay.
Okay, no problem at all.
I'm already that tired, so I will hopefully not blow it up.
Yeah, we killed one measurement objects during our webinar series, but yeah.
Collateral damage.
Collateral damage, yeah. So, this is how we did the measurement. This is, we also had a look at. So here again, you see the measurements that I recorded yesterday with the single cursor and the double cursor method. And now let's have a look at the switched mode power supply. We are using our beloved linear LT 1976 board, a board that never failed us so far. I can remember that we wrote our very first power supply application note with this board, and I think we have 2 or 3 of them, and they still all are working. And so this is a regulator, a step-down converter with switching frequency of 200 kilohertz, a maximum output of 1.5 amps, and I think 3.3 volts output voltage. The input can be from 4 volts to 60 volts. And we will operate it at 100 milliamps plus the 25 milliamps that go into the J2111.
Bernhard, it's already built up and running.
Oh, wow.
No smoke came out, so maybe you can show it on the screen.
I will, as soon as I get the right button for the camera. Here we are. So you see we have connected a new device. Again, we have connected the J2111 to the output. We pick up the output voltage with an oscilloscope probe connected to channel 2. However, we use a 1-to-1 probe so that we can directly measure the output impedance. And we have connected the current monitor to channel 1.
And on the left-hand side of the picture, you can see that we are currently loading the circuit in addition to the current injector with 99.2 milliamps, so 100 milliamps over our load resistor.
Why are we only using 100 milliamps when this thing can do 1.5?
Well, and I think here I have to cite Steve, and he always said no load is no good. And this circuit shows its worst stability at low load conditions. So we set the load to a low load condition. Otherwise, it would have a phase margin of more than 90 degrees, and we wouldn't see any peaking in the output impedance. Okay.
So, and you gave it also a high supply voltage of 13 volts. So to make sure that it has enough headroom, so it has really nothing to do. And if a regulator has nothing to do, it gets bored, and then it results in a bad phase margin, something like that, huh?
Right.
Okay, so let's switch back to the measurement. So, there we already have a result, and immediately you can see that now we have some noise. This is a switcher, so there's naturally more noise, and so it's very difficult to find a peak. I will switch off the memory because this is from a different board. So, but now we need to get rid of this noise here in this area. So,
and now I think we have to reduce the receiver bandwidth since we want to pick up less noise from the switching.
Absolutely. So let's start with a receiver bandwidth of 30 Hertz.
Then, of course, the measurement will be slower, but also less sensitive to the noise.
Yeah, and we can already see that this helps us a lot in the peak of our QTG. So now I will move my cursor 1 to the magnitude peak, and now I will move the cursor 2 to the group delay, Q of the group delay peak, and so it seems that we have 60-degree phase margin here.
Okay, I think that's fine.
Okay, but you told me that it will get much better, so that we will lose the peak when we increase the output current, so please do that.
Okay.
So
let's use 0.6 amps, 600 milliamps, and let's see what the output impedance looks like.
Okay, so we have 600 milliamps, so you can see it here on our Keithley, and now you can see that we get a comparable picture like we had before when we had only the electrolytic capacitor connected. So the curve, the peaking is reduced here, and we see already, even if I move here to the maximum and here to the center, we get this bigger than 71 degree. So mission accomplished, I'd say. Definitely. Okay, there is a question. Okay. So,
what's the question, Bernhard?
If I need to check the stability of low loads and the converter is in burst or pulse skipping mode, then how do you do it?
I think that's a question maybe Steve can answer. Burst and pulse skipping modes are always bad when you talk about linear models and stability. Steve, what's your opinion on that?
Well, there are a couple things that you need to consider, but the first is that when the converter goes into pulse skipping mode, it's not truly a linear circuit. And so that doesn't mean that we can't measure stability, either non-invasively or directly. What it does mean is that we're going to measure the average of the stability. And of course, for very light loads, the J2111 isn't necessarily the best method because that requires 25 milliamps of bias. And so at very low currents, the single port measurement might work better. We've supported many different applications. There's even one called predictive envelope balance modulation, which has no linear scheme at all. And yet they asked us if we could measure the stability of their regulator using predictive energy balance. And we did. So the relationship between impedance and stability is fixed because we know that the closed loop performance is equal to the open loop performance divided by 1 plus t, where t is the transfer function or the control loop gain. And so there is always a direct relationship between stability, open loop performance, and closed loop performance. So independent of whether or not the regulator is in a pulse skip mode, we can still get a measure of average stability.
Okay, thank you. Thank you very much, Steve. I think if you do that, then you need to set the receiver bandwidth quite low to have enough average time if you really want to perform this measurement. Is there another question maybe coming?
No, so far not. So,
in this case, we would like to thank you very much. Feel free to ask questions over the chat. We will be here for some more minutes. And if you don't want to ask a question now, or if you have a question in future, feel free to send it to info@omicron-lab.com. We try to answer. If we can't answer, we will forward to Steve. And he normally is very nice and answers.
Very responsive. So thanks a lot, Steve. Steve, you saved our butt many times already.
Oh, thanks very much.
So we just look at the chat, but so far nothing has popped up. Again, think about if you want to own a limited edition VRTRS 1.5 board, do not hesitate to send us an email after this presentation to info@omicron-lab.com. Check out our webpage for application notes. And yes, if there is something, we are there to help. Just send us an email. If too many emails arrive at the same time, we will give you an indication until when we can look into your topic.
And we will have another webinar in half an hour. Well, actually, we don't hold it, so this was the last one for us. We can
have a beer now?
Open a beer now. The next webinar will be on automated power supply design, and it will be held by Ali Shirsova. He is the designer of the software, and he would like to introduce you to the software.
Yeah, so it's a quite cool presentation, and Ali is a gifted speaker like Steve, so it's pretty cool to watch him. So if you want to dial in, we will open the webinar in about 15 to 20 minutes.
And Steve, something you will enjoy, we got a response from a customer who said, I first learned of the Bode 100 from a Steve Sandler article, and now we have one. So thank you very much. This is great feedback. We love that.
Thumbs up.
Absolutely. So, well, in case there are no more questions, we'd like to thank everybody for staying with us and for investing your time to listen to us. We plan to do some webinars again, but possibly not 12 webinars in 48 hours like we did this time.
No, for sure not anymore.
So we possibly will spend 3 days instead of just 2, and maybe only 1 topic a day. But we plan to do this again, and possibly again in November.
Well, thank you very much. Either have a nice evening if you're in Europe, or have a nice day if you're in the States. And see you in our next webinar.
And Steve, thanks a lot for your help.
Oh, thanks. Thanks for a great webinar, and love the mustaches.
Yeah.